So this is the second part of the Math 348 final exam review on game theory. This is the revised final exam set. So we're only looking at two-person zero-sum games. And in problem 1, we have a game where player 1 has 3 strategies and player 2 has 4 strategies. And this is the payoff matrix. So prove that for player 1, there's no strategy that dominates another. Well, the player 1 strategies are the rows. One row dominates another if every number is greater than or equal to the corresponding number in the next row. So 7 is bigger than 6, but 3 is not bigger than 9. 7 is bigger than -2, but 3 is not bigger than 11. So 7 doesn't dominate anyone. 6 is bigger than -2, but 9 is not bigger than -11. So player 1 has no dominant strategy. What about player 2? So for since this is the payoff matrix for player 1, a big number for player 2 is bad. That means that player 2 is losing a lot. So 11 is bigger than -2, but 3 is not bigger than 7. 11 is bigger than 3, 9 is bigger than 5, 3 is bigger than -1. This row, this column, strategy 2, dominates strategy 3, but for player 2, that means this is bad. So player 2 will never choose strategy 2. We can cross that one out. Let's see. 6 is bigger than 3, but -4 is not bigger than -1. 6 is bigger than -2, but -4 is not bigger than -7. So for player 2, we can eliminate, let's say, erase strategy 2, because for player 2, 3 dominates 2. That means 3 is less than strategy 3, and every coordinate is less than or equal to strategy 2. Well, how do we pick the optimal strategy for the players? Using the minimax strategy. So for player 1, the minimum, that is the worst that player can do, is lose -2. For strategy 2, the worst player can do is win 5. For player 3, the worst strategy for player 1, the worst result from strategy 3 is to lose 4. So of these minima, the maximum, the largest, is 5. So this is the maximum of the mins, the maximum. So player 1 will choose strategy 2. What about player 3? Sorry, what about player 2? Player 2 looks to see how much he or she can lose and try to minimize that. So with strategy 1, the worst player 2 can do is lose 7. With strategy 3, the worst is to lose 5. For strategy 4, the worst is to lose 12. So which strategy gives the best result for player 2? Well, the one which minimizes how much that person can lose is 5. This is the mini max. It's the smallest of the maximums. So player 1 chooses strategy 2. Player 2 chooses strategy 3. And the result is player 1 wins 5. That's the optimum strategy. Is this a saddle point? So in the second row, this is the smallest number. In the third column, this is the largest number. So this 5 in row 2, column 3 is a saddle point. The value of the game is 5. When each player picks his or her optimum strategies, player 1 wins 5. It's not fair. In a fair game, neither player wins or loses. So it's not a fair game, but there is a saddle point. That's problem 1. Let's look at problem 2. Problem 2, for player 1, there are 2 strategies. For player 2, there are 2 strategies. And the payoff table is 1 minus 2, minus 3, 4. And there is no dominant strategy for player 1 or player 2. 1 is bigger than minus 2, but minus 3 is less than 4. 1 is bigger than minus 3, but minus 2 is less than 4. There's also no saddle point. Right? The smallest number in the first row is not the biggest number in this column. The smallest number in the second row is not the biggest number in this column. So we have to use a mixed strategy. Let's say player 1 chooses strategy 1 with probability x1, and player 1 chooses strategy 2 with probability x2, where x1 plus x2 equals 1, which is the same as saying whatever x1 is, x2 is 1 minus x1. Now, what are the payoffs to player 1? If player 2 chooses her strategy 1, the payoff to player 1, so with probability x1, player 1 wins 1. And with probability x2, player 1 wins minus 3. That means loses 3. So this is x1 minus 3 times x2, which is 1 minus x1, which is 4x1 minus 3. And if player 2 chooses strategy 2, player 1 expects to win how much? With probability x1, the player 1 gets minus 2. And with probability x2, player 1 gets 4. So this is minus 2x1 plus 4 times 1 minus x1, which is minus 6x1 plus 4. So if we sketch a graph, we're going to solve this problem graphically. If we sketch a graph of what this looks like, we have the following. So we're graphing the payoff to player 1. So as x1 goes from 0 to 1, the payoff to player 1 is 4x1 minus 3. line that looks like this. This is the line 4x1 minus 3. If the player 2 chooses strategy 2, the payoff to player 1 is 4 minus 6x1. So this line is minus 6x1 plus 4. So for whatever probability x1 chooses, player 1 chooses x1, player could lose this much or this much. And if you want to so if you pick any probability other than this point of intersection, player 1 could get this much or this much. It's worse than this. So you want to find the point, the probability right here where these two lines cross. 4x1 minus 3 is minus 6x1 plus 4. That's the same as 10x1 equals 7. x1 equals 7 over 10. So x2, which is 1 minus x1, is 1 minus 7 over 10 is 3 over 10. So player 1 should choose strategy 1 with probability 7 over 10 and choose strategy 2 with probability 3 over 10. And the expected value of this game to player 1 is 4x1 minus 3 when x1 is 7/10. 4 times 7 over 10 minus 3 is 27 over 10 minus 30. 10 is minus 2 over 10. It's minus 0.2. So when player 1 chooses the optimum strategy, the expected value is negative 1/5. And if you did the same analysis of the game with respect to player 2, you would get the algebra would be different, but you would get exactly the same result. In fact, let me do that because that's the second part of the problem. So let's look at this game from the point of view of player 2. So this is the payoff matrix. Y1, Y2. So Y1 is the probability that player 2 chooses strategy 1, and Y2 is the probability that player 2 chooses strategy 2. So in this case, if player 1 chooses strategy 1, then player 2's expected winnings would be 1 Y1 times minus 2 times Y2. And again, Y1, Y2 plus Y2 equals 1 because these are probabilities. So Y2 is 1 minus Y1. This is Y1 minus 2 times 1 minus Y1, which is 3Y1 minus 2. And the expected winnings for player 2, if player 1 chooses strategy 2, is minus 3Y1 plus 4Y2, which is minus 3Y1 plus 4 times 1 minus Y1, which is minus 7Y1 plus 4. And if we make a graph of this, so 3Y1 minus 2, so that's the line with y-intercept, with the intercept 2 here. And it goes up with slope 3. That goes up here. So this is the 0.13. And 4 minus 7y1 it comes down to there. This is minus 3. Sorry, this is 1 minus 3. So this is showing how much player 2 will lose. And for a given y between 0 and 1, he could lose as much as this or this. And if you want to minimize the loss, you choose that point. That's the point where these two lines cross. 3y1 minus 2 is minus 7y1 plus 4. So 10y1 equals 6. So y1 is 6 over 10, or 3/5. So y2 is 2/5. And what is the value of the game to player 2? 3y1 minus 2 is 3 times 3/5 minus 2 is 9/5 minus 2 is minus 1/5, or minus 0.2. Exactly what the result we got for player 1. And the minimax theorem says that you always get the same result with respect to either player 1 or player 2. So that's problem 2. What about problem 3? So in problem 3, we have a game in which player 1 has 3 strategies, player 2 has 4 strategies. You can't use the geometric method, the graphical method I just did, because that works only when at least one player has 2 strategies. 5, 4, 0, 1 is the payoff matrix. 0, 3, minus 2, 4, 4, 5, 3, 2. So the problem is to convert this game theory problem into linear programming problem. So let's say for player 1 chooses strategy 1 with probability x1, strategy 2 with probability x2, strategy 3 with probability x3. And because these are probabilities, x1, x2, and x3 are non-negative, and the sum is 1. And what we want to do, so for player 1, if player 2 chooses, so this is player two strategies. If player 2 chooses strategy 1, player 1 can expect to get 5x1 plus 0x2 plus 3x3. That would be the expected earnings. We want to maximize that. Say greater than or equal to something, let's just call it B. In the case of player 2 choosing the pure strategy 2, the expected winnings for player 1 are 4x1 plus 3x2 plus 5x3. We want that to be B. We have 2 other inequalities. 0x1 minus 2x2 plus 4x3 greater than or equal to b, and x1 plus 4x2 plus 2x3 greater than or equal to b. So then instead of using the letter v, let's call this x4. And to say that this is greater than or equal to v is the same as saying that this minus x4 is greater than or equal to 0. And we do that for all of these. And what we want to maximize is the objective function z equal x4. And x4 we want to be greater than or equal to 0. So this is now linear programming. We have a set of equalities and inequalities, 1, 2, 3, 4, 5 of them, non-negativity conditions, and the objective function we want to maximize. So this is the linear programming problem. Let's use Maple to solve it. So it's really easy when you're using Maple. Let's switch to the, here it is. Just this one line. So I want to maximize x4 subject to the following conditions. x1 plus x2 plus x3 is 1. 5x1 plus oops, I wrote this down wrong back over here. 4x3 minus x4. These are the inequalities corrected. These are the non-negativity conditions. And this is what I get as an answer. So the answer, this means this is 10 to the minus, it means this is basically 0. And if you recognize the decimal representations of fractions, this is 1/7 and this is 6/7. So let me just write that down. x1 equals 0, x2 equal 1/7, x3 equals 6/7, and x4, which is my z, is 2.2857. So let me stop the share. Yeah. So the linear programming maximize function in Maple says if I choose the probabilities x1, x2, and x3 as 0, 1/7, and 6/7, this is the optimal strategy for player 1. And player 1 wins on average 2.2857. This is also by the minimax theorem the best player 2 could do also when player 2 chooses an optimal strategy. Well, that's the answer. And that is the end of this little review.